theorem. Here's a theorem. Turns out the V has H as a subspace in there, right? And H perp as also the subspace. And they happen to be direct sum, and that's it. This is a nice decomposition because this I call is a nice basis extension. Does that make sense? If I have H, then I can extend the basis all the way to V. When you were doing this business before, it was just random pick. Just grab anything that's out there. It's linearly dependent, grab out there. So when you're actually doing this in the Jordan canonical form, you meant with the long chain of this n minus lambda I to the Lth power, you have to do this business. And in that, we have to rely on this augmented form, and it's a random pick. If you look at it here, if I have a subspace H, if you happen to be in the inner product world, it gives you a very nice complementary part, which is not random. This is a canonical, this nice canonical, this is a mathematical jargon, appears in many parts of the mathematics. It tells you this is not a random thing we're doing. It is a very right choice. It's a good thing. It does not depend on, a choice of a basis or anything. So there are lots of things out there. You can fill in H, direct sum of something else will be still V. Remember, if you have it here, subspace H in there and in R3, something sticking out like this, together they form a direct sum. There's a line there. This one-dimensional linear space with there is a direct sum. There's no intersection other than 0. And there are lots of other things there. This line will do, but there's a good one, right? What is a good one? The normal line right above that, and that's the generalization of that. So one thing the inner product serves here is, let me write down, inner product open up a world of a huge geometry world, which is how we started. Lots of example I did. That gives you huge inspiration to physics. That's one thing that serves. Next thing was we focused on the metric, and we did something called functional analysis, computing the coefficient of a trigonometric polynomial that is closest to that. That's a free analysis. That's the functional analysis, right? To approximate with respect to the matrix with other things. Now, third thing it serves is that orthogonal decomposition. That's what this one is. It's a very, very important, nice theoretical tool. It's really easy to say theoretically there is an orthogonal complement H perp, and theoretically it serves a huge in the topology and cohomology and higher algebra. Whenever you decompose it, you don't want to do it randomly. You want to do it nicely, that it preserves the property, and the best choice turns out to be always like orthogonal. If you have nothing, the usual thing that you choose out of random is the smallest one or the largest one. That is called Axiom of Choice, well ordering. If you have to pull something out when you're doing the pure mathematical and abstract business, always choose the smallest one or largest one. If you don't have it, it's usually you end up with a lot of chaos. And here in the vector space, you have to choose in a complementary basis. You always choose orthogonal complement. If you're not in an inner product space, then it's ugly business. But if you're in inner product space, there's a nice one like this. Okay? Let's see why this one is true. And this one is also under the condition that dimension is finite. H perp might be infinite because we're allowing V to be infinite. But you will see where this condition is kicking in. Right? Proof. Do you remember the direct sum proof? What we have to do? First, we establish the direct sum property, right? So here's H, sum H perp. Remember that guy? Is H direct sum. If, right, intersection is trivial. All right, let's do that. V is coming from H, say that, and V is also in H pub. Because it's a finiteness, we have a projection map, right? We do have a projection map. So let's see, what do you know about this fact? And knowing that this fact, what do you know about the projection of this one? What's that? Are you sure that's going to be V? Chris is very sure. That is it. So we got that. What about this one? What do you know about the projection of this one? Why is it 0? That was a kernel. That was null space H pub, right? But these two things has to be the same. So V must be 0. Okay? So we use the dimension H being, like, where did I use this dimension being finite? Maybe we didn't use it here. Or did I use it? This pH, orthogonal complement, is only defined if H is finite. Remember that part? Right here? It is only defined when your H is finite. If H is infinite, just as a polynomial, there is no projection. Okay? That was some hard advanced problem there. There's no U0 in there. All right, so we got that part. What is left? We have to show V is actually H plus H perp. You don't care about the direct sum now. Just got to be able to write that every element in a V as a sum of two elements in H one element and H perp element, right? Okay. So let's do that. Here's prove this one. V is coming from V, and we have to come up with this H and H perp. And write that down and show that this satisfied all the conditions. That one came from H. The other one is really orthogonal to everything H. So, in your instinct, what is this H is going to be? Just out of nowhere, I give you V. You know nothing about it. How are you going to find that H? What's a good candidate? Maybe this notation will help you. U0B is a projection. Okay, I have V just projected onto H, right? That's that. And it should work out. So then what is that W0? If this is, we want to write this one as a sum. So if that's U0, then W is whatever the remaining part. Does that make sense? So that V is a U0 plus W0. And we know U0 came from H. Why is that? So first you have to show is that, all right, U0 is H. Why is that? Since U0 is the image of V under projection map. Does that make sense? If you project something, you land on an H, obviously. How about the other one? Why is this W0? Is this W0 if it came from H perp, it should be orthogonal to everything that is in H, right? That is in question, correct? So let's do that. How do you know that? What is W? W0 U is, what is W? V minus U0, right? U0, like that. But what was U0? That was the orthogonal projection. But what was the definition of orthogonal projection? Remember definition of orthogonal projection? Orthogonal projection is U0, where U0 satisfies what condition? v minus u0 is perpendicular to everything in the v. This is the defining condition of a pH, u0. So this is the defining condition of what? u0, the orthogonal projection of v. So there, that whole thing is a condition. Not only for few u, but everything that is in H. Okay, so v is u0 plus w0, and u0 came from H. w0 satisfies this condition. If you inner product with anything in u, it's always 0. Therefore, we have this orthogonal decomposition. That is something nice came out of inner product space. With just a vector space structure, completing this, if I have a subspace, we complete the other one. There's no good choice. You just have to do it in random, and this one is a very good orthogonal choices. Does that make sense? And here's a corollary. And I will leave that as a homework problem. Not in a random condition. Under this condition, H is a so if dimension of H is finite, then H per perp is back into H. The tricky part is that we're considering perp orthogonal complement of something which has infinite dimension, right? Dimension is infinite. H perp potentially have a dimension infinite, right? So you have to be in that context and try to show. This context is actually this result itself. V is H, orthogonal H perp. And you have to show that everything that's orthogonal to every element in here is actually H. That's what you have to show, right? Does that make sense? Yeah. Let's see, I have one more statement I wrote down in here. Yeah, this is also another corollary. If the dimension of V is always finite, then of course H per perp is the subspace H is going to be finite dimensional, so this holds also true. So people introduce this statement in courses like this. In a finite dimensional space, H per perp is going back to itself, but you can do a little bit better. If the H is finite dimensional, then per perp going back to H. So this is one of the things that's nice about. And also in here, the remark I wrote it down is that dimension of H perp in this context still can be infinite as well. Could be finite if the dimension of V is finite. But the direct sum was an interesting statement there. So, so that thing is there. So I wrote down all the combination. All right. So let me review this linear. That was a third 1, 2, 3, and fourth application is coming out. What is good about having this inner product is the following. More applications.